all those extra electrons in those outer shells that just love to move, basically the charge carrying, basically the mobile electrons. Mobile electrons now have a push to start moving. As the electrons move, they create a current, which creates a magnetic field.
Would it do the same, would it do something very similar with aluminum?
It should. And with this, I finally accidentally bent this thing. I might have to go out and buy aluminum. I bought this more than a decade ago before copper prices got out of hand.
I would say it's expensive now. People rip those out of walls.
This is physics equipment though at this point. Actually, the next step is I might get the school to pay for it instead of my going to the hardware store to buy it. Now, the second piece of this is it's causing a current in the copper pipe, which creates a secondary magnetic field. So if this is my copper pipe here, and I got north downwards on from the initial magnet, which way is the current flowing in the pipe?
Down.
So you're having current flow this way.
I think so.
What would be the magnetic field created by a current flowing that way? So it would be in over here and out over here, and I guess flowing around like that, right? Why would that oppose this magnet?
Wouldn't there be something that's forcing it to go up?
Therefore,
To slow down from gravity pulling down?
okay. So which way would the current need to flow in order to keep this to try to force this up?
From the opposite of what you got up there.
If I do that, which I think was what you were shooting for, okay, so now the current's flowing out over here and in over here and this way. So why would this magnetic field oppose this magnetic field?
I was just thinking gravity, but because if something's falling and it falls slower than what gravity's falling at, then some force has to counteract on it to go.
Okay, so if I've got a north pole pointing downwards, what's gonna cause it to not want to go down? Or at least slow it?
A south pole.
I think a north pole.
North pole
Or
with
north pole.
opposites.
All right, so if I've got its north pole right here, downwards, I would need,
Another north pole.
so what would create a north pole pointing upwards?
The charge.
Flowing which way? Which way does the current need to flow to create a north pole that's up?
If you're looking at the wire from the top, it would have there if you're looking at the pipe from the top, the current is flowing clockwise. Is that right? Or
So clockwise,
That means it's going.
I guess counterclockwise?
is it looking from overhead point of
Oh,
view?
over here.
So counterclockwise would be this way and clockwise would be that way.
Yeah.
Okay, so you're going, you said clockwise first and then you said counterclockwise. Are you just hitting all the choices?
No, I think it's.
With the,
I think is it counterclockwise? I'd say counterclockwise.
We're looking from the top.
Yeah, because if it's from the top, if you're flowing that way,
yeah.
Yeah.
then your field curls up the pipe.
All right, so counterclockwise, so looking from the top, that means it's flowing around like that. So flowing this way.
Yeah.
So that creates a north pole going up,
Yeah.
which is what we want. Yes.
Okay.
So it would create so the current is not flowing up or down. Current is flowing around. So I want it going around like that, so it's coming out, so the current's flowing out there, in there, so this is the current flow, which creates a north pole here and a south pole here.
Would it spiral that direction going down if it fell? Or is that?
Would what spiral?
Would the magnet spiral going down the,
In the
down
direction.
to, yeah, in that direction?
Oh, in the direction of the current?
Yeah.
No, going back to what I said earlier, if I could drop it perfectly, it would just fall straight down. There's nothing, there's no, in order to get this to spiral from nature itself and not from me, you would need to have
Or I guess.
some sort of torque acting on it.
I mean, sorry, not a spiral, but a spin.
Yeah, I don't think there'd be any reason for it to spin. Because you would need some force pushing it one way or the other, and you basically have these, the trouble with two-dimensional drawings, you have, if you think about magnetic fields, let's separate that a little bit. This has magnetic field lines going this way, this going this way. I mean, in an ideal situation, if I could drop it perfectly in the middle, perfectly straight, then they would just balance each other perfectly. They wouldn't be forcing it off to one side or the other. All right, so let's think about this in terms of Faraday's law. I mean, we did a torque that created an EMF, a voltage, which caused currents to flow, which caused a secondary magnetic field. This is the change in the magnetic flux. As it falls, just in front of the magnetic flux is increasing. Well, actually, anywhere in front of the magnet, before the magnet gets there, the magnetic flux is increasing. The current that is induced will create a magnetic field that opposes the increase. Nature wants everything to stay the same. So as it falls, if my magnetic flux is increasing, this current will try to reduce the magnetic flux. Let's think about on top. As the magnet passes this point, what's happening to the magnetic flux above it?
It's getting weaker.
And so since this is becoming negative, the EMF that's created will create a secondary current which tries to bolster it up. It's not always trying to reduce things, it just wants to put everything back the way it was. It's kind of like the electric inertia, electromagnetic inertia. So as it falls, we have it wants to increase the magnetic field. Because the magnetic flux is dropping, it's not going to change the area of the pipe. Its only choice is to change the magnetic field. And so it is going to create, well, my magnetic field is pointing downwards above it. And so it's going to create a magnetic field. The induced current will create a magnetic field in the same direction, which means this current is flowing this way. So below it's creating it like that, above it's creating it like that, which puts a north pole here and a south pole here. So not only do you get the repulsion below it, but you get the attraction above it. So we got two things going on there. The implications of the negative sign are that nature is always trying to mitigate the change in the electric flux. I want to do one more magnet in the tube. And then we'll actually get to some more classic chord problems. They go by several names. The rattlesnake eggs is the one that, at least when my son bought them, is what they were called. I have no idea if he knows that I took them, but he's almost 30, so he can deal with it. All right. I'm going to drop this through. And again, let's drop the marker. It's been a while since I've dropped a marker through. All right, now I drop this through. It didn't seem to slow down a whole lot.
Mass.
Why?
Mass.
And the fact that it's not a weaker magnet. A weaker magnet is not explaining really why it fell the way it did.
Shape. I don't know why, but I feel like it has to do with the shape. There's not as many like sharp edges and corners.
No, actually, I have, it's slightly more cylindrical than this, something called cow magnets. I don't know if you've heard of cow magnets. I'd been told about them. It's like a cylindrical magnet, except it's sort of curved on the ends. So like this, except slightly more cylindrical. And I was in South Carolina. I was out in rural South Carolina, and we stopped off at this, a store that would have them. And I walked in there and I said, "Do you have any cow magnets?" And she goes, "What?" I said, "Cow magnets." "What are you talking about?" "Well, it's a magnet that the cows eat so that if they eat any metal, the metal sticks to that and just stays in the first stomach as opposed to just ripping through them." "So you want to get your cow to eat a magnet? Do you have any cow magnets?" "No." "All right." I'm on my honeymoon in Wyoming and just happened to stop by a store which would have these things. I said, "Do you have any cow magnets?" She goes, "Oh yeah, they're right there." So apparently it's a Western thing, or at least not that South Carolina thing. So, the shape of it, I have other ones which would slow down, and I tried to find them in my office and I can't find them. So unfortunately, the shape of it is not the issue there.
Lost your honeymoon present.
Why not?
I think it has to deal with something with mass. There's nothing that's really much different from it. I mean, I feel like the magnet's almost the same strength, maybe stronger than the other magnets you've thrown down at.
Strength of the magnet is really not the issue here.
Yeah.
Is it the length in comparison to the length of the copper pipe?
No, the shape of it is not the issue. The head, that completely failed. Hopefully it wasn't on camera. That's the head right there.
Is it on the side compared to being,
That's the difference.
okay.
I guess you could say the shape has something effect to it, the fact that it's not gonna rotate over, but as it's falling down, north-south is on the sides here, and not top and bottom. So you don't get the same effect. You have, well, basically the magnetic flux is
It's kind of like
probably
this.
zero the entire time. Before I write on the board with that. So if there's my copper pipe and I've got a north coming out this way and a south coming in there, so that's my north-south. Any surface I have a north going in and I have south coming out, so any flux I would have there, I would have the opposite flux there. So I think ultimately the flux would be close to zero the entire time.
It just falls.
What was that?
So it just falls.
Yeah. All right, any questions before we actually get into some math parts of it?
If that pipe were big enough to accommodate that flipping, would it want to stay in a north-south position, up and down?
But, they're big enough to accommodate it that way?
Yeah. Does it want to orient itself north-south, up, down?
I don't think that there's enough of a pull to it. It is let's see, so the Earth's magnetic field approximately, depends on where you are on the Earth. I think that's north that way. So the magnetic field is roughly running that way right now from the Earth. Which means that the magnet would want to orient so that north would be over here and south would be over here. I think it would want to orient itself horizontally.
Okay, so the way it orients itself would have nothing to do with.
I would not think so. I don't think so. If you find something to the contrary, send it to me or show it to me. But I don't think it would.
If you laid the pipe down and you inserted a magnet into it, would the magnet float?
Oh, all right, so let's talk about floating. There's something known as the Meissner Effect. There's another one, I can never remember what the other effect is, but there's two of them that are very similar to each other. But we'll stick with the Meissner Effect. I have a magnet here. And generally, the demonstrations I've seen, it's a small magnet, roughly about that size. It can't be too heavy. And we have a superconducting material down here. So it does need to be superconducting. So that the resistance is as close to zero as you can get. It's generally considered to be zero resistance. I'm never quite sure whether it's zero resistance or just too small to be measured. As it falls, we're going to get a change in the magnetic flux here, which creates this countercurrent, which then creates a magnetic field to oppose the fall. And so then it will fall, it'll stop. When it stops, you no longer get the change in magnetic flux. Actually, it'll push up a little bit. You no longer get the change in magnetic flux, so the current's going to drop, so it will start to fall again. As it starts to fall again, it creates the magnetic field and so forth. And so you can get it to hover like that, to the point where you can, if you had oh, there it is. Probably not metal, that'd be a bad choice. Take something plastic, you can tap on that and it will spin in place.
Like an ice, or like either ice or space effect.
Yeah, something like that. So there are demonstrations out there which do this. Superconducting would, I think at this point, we're down to 70 Kelvin, or up to 70 Kelvin, I guess I should say, of how warm we can get it and still have superconductivity. There's a huge breakthrough in the 80s, and then there's been sort of creeping along since then. I'm gonna see if I can get my hands on the actual, on it quickly, otherwise I'll move on. Oh, maybe in the other notebook, when we were talking about resistance. I don't think we've topped 100 Kelvin, but there was a huge breakthrough, there's a big leap, and they thought, oh, all right, room temperature superconductivity, here we go. And it just basically stalled there. There have been some incremental increases, but nothing significant. So room temperature superconductivity, I think, only occurs in Alaska in the wintertime when you open the windows. Yeah, so, and this will last as long as whatever you're pouring onto this to keep it that cold, like liquid nitrogen, as long as that's still there. So you either keep pouring liquid nitrogen, or at some point it's all going to evaporate and this will fall.
Question, as that temperature goes up, does that magnet fall closer?
I was thinking that it fell slowly at first and then there's a sudden drop, but I'm not sure, actually. Presumably at this point, there's a video out there where somebody's done this.
Somewhere, because to me it doesn't seem like it would just hit like a certain temperature and be like that, because that would be whatever your superconductivity barrier would be.
Because once you introduce resistance into it, suddenly your current is going to drop. As it heats up, the resistance is going to increase faster. Yeah, but then as it falls faster, it's going to create. Yeah, I'm floating back. I'm sort of leaning towards it. It's a much slower descent than my first thinking is, but I don't know. All right, other questions right now? All right, let's get into some math. And I did something with the eraser. There it is. I got a dead piece of wire here. There's not a complete circuit, it's just a piece of wire that's bent. But on top of it, I can complete a circuit by putting another wire. This is a movable wire. Of course, I'm going to bathe this in an electric field. I'm now going to move this wire to the left at some speed v. which way will the current be forced in that wire? Or which is the higher potential, here or here? Let's take it step by step. I know whatever happens, whatever current that I induce, it wants to reduce the change that's about to take place. So as the wire is moving to the left, is my magnetic flux increasing or decreasing? Do we need to take a little break?
Is it decreasing because distance is decreasing?
Because the distance is decreasing?
Yeah.
Which distance are you talking about?
Distance from the movable wire, or from there to there.
To the close in the wall.
Why does the decreasing distance mean that my flux is decreasing?
CED. Or any other variable.
Sorry, say it again?
CED or any other variable.
Say it one more time, because what I hear you saying is, oh, you said CED?
Yeah.
Oh, the parallel plate capacitor bit.
Yeah.
Wrong path to go down.
Okay.
Is it because DL and the D flux is proportional?
Not for that reason. Oh, well, let's see. Yeah, no, depends on what you mean by that, but I'm gonna go with no for right now. Let's go down a different path. All right. What was the question I asked? Because your answers aren't really matching what I thought I asked. So what did I ask?
As the wire is moving, is the magnetic flux increasing or decreasing?
Okay,